Hi everyone, Mr. Boltri here, bringing you video 7.2. We're going to talk about universal gravitational potential energy. To do that, we're going to review what we already know about gravitational potential energy, and we're going to derive a formula for universal gravitational potential energy, and then use that formula to calculate the escape velocity for an object. So what we already know about gravitational potential energy is we've been calculating it on the local level. And what I mean by that is that on the local level, we can treat the force gravity as constant, which is, so this formula, the change in gravitational potential energy equals mass times the acceleration due to gravity times the change in height, is true in a constant gravitational field. So what I mean by that is we learned in the last video that the force gravity actually changes based on how far you are away from the center of mass of the Earth. So when we actually move, the force gravity does change, but the change is so small when we're talking about a change in height of 10 meters or 100 meters, then we can treat the force gravity as constant. But when we talk about moving hundreds of thousands of meters away, then we can no longer treat the force gravity as constant, and we can no longer use this formula. Two other things that we need to remember for when we are doing local gravitational potential energy calculations is that we had to establish a zero line. And we also know that force gravity acts as a conservative force, meaning that it does not change the total mechanical energy of the system. And so this is important to remember when we start talking about gravitational potential energy. The universal gravitational potential energy is what we use to talk about the gravitational potential energy sort of beyond the local level of the surface of the Earth. So you'll notice that on sort of when we're close to the surface of the Earth, we can treat locally the force gravity as kind of constant. As we get farther and farther away, the force gravity gets smaller and smaller, proportional to the square of the distance between the centers of masses of the objects. So if we're talking about the gravitational potential energy, we cannot use that local formula anymore. And the biggest reason for that is because the acceleration due to gravity is not going to be the same when you're so far away, because the force gravity is not going to be the same. It's going to be changing with respect to the distance between the centers of mass. But the one thing that does make this really convenient for us is that when we use the universal gravitational potential energy formula, zero is established for us. Zero gravitational potential energy is when the object is very, 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 very far away from the planet. And so there's going to be basically no force of attraction. So there's going to be no gravitational potential energy. So there's sort of a universally defined zero gravitational potential energy, which is based on being very, very, very far away from the planet. And so then the other thing to know is as you get closer to the planet, the gravitational potential energy gets bigger, proportional to the fact that the force of gravity by the planet is getting bigger. And that number is a negative number, which just means in this circumstance, the negative means pointing towards the planet or into the planet, which makes sense and matches with what we've already learned, because objects want to have the lowest possible gravitational potential energy. And by that, I don't mean closest to zero, I mean the most negative, like the lowest. So as it gets close to the planet, the object actually wants to go towards the planet because that's lower gravitational potential energy. So that just makes all of our definitions line up with everything. So now let me quickly derive the formula for gravitational potential energy, which just shows an application of calculus. But the most important thing to remember is the formula, which we're going to get to at the end. So we can start with the idea that force gravity acts as a conservative force, which allows us to use the formula, which is really important and not on our formula sheet, that the derivative of the gravitational potential energy with respect to displacement equals the negative of the force gravity. So we've used that to calculate the sort of local gravitational potential energy, but now we're going to use it to calculate the global gravitational potential energy. So what I can do with this, if I'm trying to solve for gravitational potential energy, is I can integrate both sides with respect to r, which on the left side is going to give me the change in gravitational potential energy. And then on the right side, I'm going to integrate it from some initial displacement to some final, or the r stands for the distance between the centers of mass. So then what I can do from here is I can substitute in our universal gravitational force equation, my g_mm over r squared equation. And so you'll notice that we have the negative over here from how we define the derivative of the gravitational potential energy function. And then we have the negative over here for the force. And that, again, just means that we are defining, so before we said the force gravity points down, which we typically say is negative. Now, since we're doing some more universal stuff, we're going to say that the negative direction is pointing in or towards the planet. So towards the planet or in is going to be in the negative direction. So that's why I have this negative here. So then the next thing I can do is I can factor out some of the constants, some of the things that aren't changing with respect to r, with respect to the distance between the two centers of mass. So my negative and negative, I have a positive, and then these are all just constants in this situation. So then I'm going to integrate 1 over r squared from my starting and ending distance between the centers of mass. So what that looks like, just you might want to practice doing this integration for yourself. And don't forget that this is 1 over r squared. We could also write as 1 over, as r to the negative 2. So when you do that math, the integration, you get a the constants stay the same. And so then you get negative 1 over r, or negative r to the negative 1, integrated from our starting point to our ending point. So then when we substitute those in, we get this basically, which is important because then we can make one other important assumption, is that if we take our initial distance between the two centers of mass, r is infinitely far away, just like very, 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 very far off in the middle of the space, then our initial universal gravitational potential energy is 0. So I can basically strike this out and also get rid of my delta, and just say that my final gravitational potential energy is equivalent to this formula, which you'll see on your formula sheet written as this. And so basically it's saying RF is R, and the universal gravitational potential energy final is UG, is basically saying, hey, we can ignore the 0 gravitational potential energy at the very beginning. And this is just basically telling me whatever is the gravitational potential energy at any given time. So this is the formula that you will see on your formula sheet, and it's important to know. Now, some common things that people mess up when using this formula, 2 things. 1, people like to forget the negative, but the negative is really important because that's the reason that things go towards planets instead of away from planets. And then they like to put a r squared in here because they're thinking of the force of the gravitational force formula, and this is the gravitational energy formula. So make sure that you don't have the square in there. And you can remember it doesn't have the square in there because we got to it by integrating the force, which takes the squared in the denominator to a just power of 1 in the denominator. But this formula is really important to know and useful. So now let's look at sort of how things work locally up top versus universally down at the bottom. So if we have locally, the force gravity was mg, and the gravitational potential energy was mg delta h. And so we got here by multiplying by a change in height. So we can, it sort of works almost exactly the same way, is that we multiplied by an r to get from the universal gravitational potential energy, universal gravitational force to universal gravitational potential energy. So that's sort of how those 2 things are related. Is it, again, like when we were from here to here, we weren't rewriting the rules. We were just taking a specific example and making it apply in all circumstances. And then here, same thing. We were taking a specific example which only works locally, and then making it apply in all circumstances. Okay, so last thing before we wrap up the video is I want to do an application of this formula, which is escape velocity. So what is escape velocity? Well, let's say that we have a cow on the planet, and we want to launch the cow into space with enough speed, with some initial speed, such that the cow will escape the gravitational pull of the planet Earth and be out in the middle of space, far away from the gravitational pull of the planet Earth. I mean, so it basically needs to be infinitely far away, or the force is going to approach 0 asymptotically. So over here we have our cow, which has a final gravitational potential energy of 0. Basically, it's infinitely far away from the planet. So what's the minimum velocity that we need to launch the cow away from the planet in order for it to escape the planet? That's kind of what escape velocity means. So we can use our gravitational potential energy formula, knowing that the final gravitational potential energy has to be 0. And we can graph it starting at here I have the radius of the Earth, because we'll say that it starts on the surface of the planet. And here I have the how much gravitational potential energy the cow has when it's sitting at the radius of the Earth. So in order to get the cow far away from the planet, we need to launch it such that it's far enough away that the gravitational potential energy is going to be zero. So we need to launch it such that it's very, very, very far away, basically, for that gravitational potential energy to be zero. And so the amount of energy that it takes to do that is called the binding energy. To get from whatever energy it has on the surface to infinitely far away, where the gravitational potential energy is zero, is called the binding energy. It's how much energy is binding us to the surface of the Earth, how much energy we'd have to overcome if we wanted to escape the pull of the planet Earth, or any planet, really. If we set the initial kinetic energy to be equal to the binding energy, that escape energy, then we can solve for how much velocity we need in order to leave the planet. And you'll notice one really cool thing about escape velocity is that when we have the kinetic energy on the left and the binding energy on the right, you'll notice that the mass of the cow cancels out. And actually the escape velocity for a given planet is true regardless for the object. So we could launch a cow or a rock or a rocket, and we would need to achieve the same escape velocity no matter the mass of the object. So then we can solve for the velocity in this equation. We get the square root of 2 times the universal gravitational constant times the mass of the Earth divided by the radius of the Earth is our escape velocity. And this is actually a formula which you do not need to memorize, but you should be able to pretty easily derive using this two-step process for the escape velocity for any object on any planet of any mass. So actually, if you plug in the mass of the Earth and the radius of the Earth, you get the escape velocity for planet Earth is about 11,000 meters per second, which is very, very fast. So you have to be going very, very fast to escape the gravitational pull of the planet Earth. So I know that was a lot, and we're going to practice using these formulas in the next class. The most important thing is you don't have to memorize the derivations. You just have to know the formulas. And I figure the best way for you to know the formulas is for you to at least have seen the derivation once. So feel free to go back and watch it. Feel free to write down and ask any questions. We'll do some practice problems with this in our next class. But right now, this is Mr. Boltri wrapping up video 7.2, and go Bears.